So let's figure out how do we go from the approximate areas to an exact area calculation. So let's take a look at this function here. And let's say I'm trying to find the area underneath this curve from A to B. So I'm trying to find this region here. How can we use rectangles to help us with that? So if we think about the strategy of rectangles and what we've done so far, if, let's say for the sake of argument, I'm just going to use right endpoints. They're usually the easier one. If I use the right endpoint, I could create one gigantic rectangle. Super easy, right? Find the area of this single rectangle, take this width here times the height, boom, that's my approximate. That kind of stinks, right? Hopefully we see that that's not a very good approximation. So to make it better than using one rectangle, well, why don't I try using two rectangles? Right, so what if I divide this in half? I use this region, and then I use this region. Maybe that's a little bit better. It seems like I could do a little bit of a better approximation, but what if I wanted to do even better? Well, the thought is, well, I could try having more rectangles. Right, so what if we instead had three rectangles? So if I divided this region into thirds, so let's say I was over here and over here, use the right endpoint there, use the right endpoint there, use the right endpoint there. I could find the area of these three different rectangles, add that together. Obviously, I could do better by having more. So what if I jumped now with this process? What if I jumped to having, say, 1, 2, 3, 4, 5? No, 2, 2, 2, okay. So what if I look at 8 regions now? If I use the right endpoint, I have this region, this region, this region, this region, this region, this region. Okay. Now notice with each of these rectangles, how good they describe the area in their region is getting better than they were when we had less. Right? When we had 1, that did a really bad job of describing this entire region. When we have 8, that does a pretty good job, right? It's obviously not perfect, but it's pretty good. But if I was to even divide this even more, let's say I was to have super skinny rectangles here. If I was to have really, really, really tiny ones, well then when I look at the areas, I would get the following. Now notice, you can barely even tell the difference between what my little areas would be, the difference between the actual height of the rectangles versus this nice smooth curve. So what it seems to be like, the more rectangles we use, the better the approximation is. Right, so the more rectangles we use, the better our approximation is. But again, these are still approximations. No matter how many rectangles I use, if I use 100,000 rectangles, it still will not be perfect. There's still going to be some error. So the question is, how many rectangles do I need to use to be able to say that it is exact as opposed to approximate? Well, the more that I need, the better. So if I could somehow use infinitely many rectangles, but you can't do that. You can't have an infinite number of rectangles and be able to calculate the area of those. But what you can do is you can use limits. So we need to use our limits. And so again, this is where limits now get to be reintroduced to this idea of going from an approximate to an exact. Going from a finite to an infinite. We saw that with derivatives, right? When we looked at secant lines, we used this kind of this limiting process to be able to have those secant lines, the slope of those, give us the actual slope of the tangent line. We're doing the same thing here. We need to use limits. Now, how we're using limits is on the number of rectangles. We're going to have larger and larger number of rectangles. So if we look back at the definition we had last time, we had our approximate area formula. This was the sum from I equals 1 to n of f of c sub I delta x. So we had this formula was our generalization for this. And as a reminder, we had this delta x. This was b minus a divided by n. So at some endpoints, divide that by n. In c sub I, that depended on kind of our choice of what we wanted to choose. So we want to choose the right or left endpoints. So when we want to find the exact area, we will take a limit. And we said the limit is that we want n to go to infinity. So we're going to take the limit as n tends to infinity, and we have this sum of I equals 1 to n of f of c sub I delta x. So when this limit takes place, I can now calculate the exact area. Now, important fact here is that we're going to need to do this first. So you need to work with the sum first. You can't take limits right off the bat. That is not allowed. You must work with the sum. We're going to simplify it, but n is still going to be floating around as some type of variable. Then once we're done simplifying this, then we're going to go ahead and take a limit as n goes to infinity. Then we will get our exact area. So this is extremely important. We're going to be using this intuition of rectangles to approximate the areas and then taking limits to get exact areas pretty much for the rest of your calculus career. So keep this idea in mind.